In this video, we'll be talking about software-defined storage. First, let's take a look at shared storage systems. Shared storage systems such as SANs and storage servers are quite popular for data center storage. Now, in this example, we have a disk array containing disks ABC that are carved out for servers ABC, and they're all connected through a fiber channel or internet switch. Now, in terms of capacity and performance, capacity is quite easy to define and distribute among tenants, especially in a multi-tenant data center. However, performance is typically tied to the SAN or server hardware and storage network and is not as easily controllable. Performance requirements can differ from application to application. So if a tenant is running a content delivery system, their performance requirements for storage is quite different from another person who might be running a transactional database. For the content delivery service, they would be more interested in peak bandwidth, whereas in a transactional database, they would be more interested in end-to-end latency for each request, as well as the number of requests that can be completed in a second. Therefore, different users may have different storage performance needs, and usually they require some specific bandwidth or latency requirements as defined in an SLA. Now, this is difficult to guarantee in the current scenario because you don't have control over performance in the storage stack. Right now, the only option is to create separate SAN systems for separate storage performance needs. In line with the software-defined data center, we'll now introduce software-defined storage. SDS allows clients to specify fine-grained capacity, latency, or bandwidth requirements as SLO. The entire storage stack is then managed in an end-to-end dynamic fashion as defined by the management software, much like software-defined networking. Therefore, software-defined storage allows for control over performance along with better isolation and dynamic control of storage infrastructure. Let's take a look at the typical I/O path in shared storage systems. Given a server, network, and a storage system that contains shared disks for the virtual machines in the server, a typical I/O path would extend from the application running inside the virtual machine, through the operating system running in the virtual machine, through the hypervisor and the server hardware, through the network, which may contain multiple forwarding devices, and then through the storage system, through its interface controller, and then finally to disk. An early example of software-defined storage is IOFlow. IOFlow is from Microsoft Research. IOFlow manages performance across the I/O path by introducing queues at each stage along the I/O path. Now, this is an example that's quite specific to Microsoft. You have a compute server running multiple guest OS in VMs, and in each VM there is a file system application and a virtual block device that is provided by the hypervisor. Now, the block device is actually an exported disk device that is running off of a storage server. The protocol used here is Microsoft specific. This is called the SMB protocol. On the hypervisor, we have the SMB client, which connects to the SMB server on the storage server. Now, in this example, what they've done is they've modified multiple layers along the I/O path, including this SMB client, SMB server, and the network driver to introduce queuing. So they have queues now at each of these layers. Now, each queue is regulated by a centralized controller, as you can see in the figure. The controller assigns data rate metrics and route at each stage in the I/O path. Now, the way in which the storage flows are controlled are by flow identifiers. Individual I/O requests have flow identifiers attached, and these can be used to identify individual requests and route them and rate control them. So here are a few example flows that were described in the IOFlow paper. Flow P1 ensures that a VM, which is VM1, is guaranteed a fixed bandwidth B. Another flow P2 could be described where extra bandwidth is available to VM1 and is allowed to exceed, bandwidth B. Flow P3 is a sanitized policy. So here the IO traffic is routed through a sanitization layer, for example, a malware detection layer. Now, you can think of Flow P3 as a default flow that's assigned to all new clients when they sign up for a cloud service. So all VMs that are from a new client and for a particular period, say, maybe a few hours to a week, since the cloud provider does not fully trust these new clients and may not be sure whether they're involved in any sort of, malicious work, they can automatically assign flow P3 so that all IO traffic gets routed through a malware detection or sanitization layer, just as a stopgap measure until they are able to trust the client. Flow P4 is a high priority, data traffic for virtual machine 2, and must be given high priority end to end. So, Flow P4, if there are other flows that exist, Flow P4 probably has the highest priority among them. And in Flow P5, multiple VMs that belong to the same client access a common pool of resources can be guaranteed a bandwidth B. So in this example, you're spreading out a bandwidth B across multiple VMs that belong to the same client. Now, these are flows examples that are made possible through, an SDS system such as IO Flow.